Well, good afternoon. It's noon on a Wednesday, which means it's time for another Iowa Learning Farms conservation webinars. Hello, welcome. I'm Liz Ripley, the Conservation and Cover Crop Outreach Specialist, and I'm thrilled to have with us today Dr. Chumki, Banik, and Santanu, Bakshi, as they are sharing some of the research that they're working on here at Iowa State University, where they're using biochar and zeolite to recycle phosphorus and nitrogen from swine manure. So if you have questions along the way for both of them, feel free to submit them to me via the chat, and we will ask them following their presentation. So without further ado, I'm looking forward to learning more, and I'll turn things over to our presenters.
Hi, Elizabeth. Can you hear me?
I can. Sounds great.
Okay, thank you. Good afternoon, everyone. So I am Dr. Santanu Bakshi. I'm working as an environmental research scientist at the Biochar Institute at Iowa State University. So today we are going to talk about our recent work and also a recent grant from the United States Department of Agriculture. So our title is Biochar and Zeolite to recycle phosphorus and nitrogen from swine manure. So in this project, so we are trying to develop an integrated approach using these two material. So 1 minute. At first, I want to talk about why are we considering swine manure. So pork is number 1 rank in Iowa in the United States, and the output is around in 2020 was around $41 billion, and so we have around 24 million on hand, and approximately 50 million produced annually in Iowa, and that total pigs produces around 1.2 gallon per day of poop or manure. So total is around 10 billion gallons annually. Now think about it, what we will do with this 10 billion gallons of manure. Obviously, swine manure can be utilized as a crop fertilizer, and it is being used I think it's several decades. So now manure in the farm, they often stored underneath the barn in the concrete pit and separated from the pigs. And this manure has more than $1 billion price tag Newton value in Iowa. Now think about farmers, as they often get their drinking water from the same source as other rural and urban residents. So obviously they care how it is used. In terms of phosphorus, manure has a lot of phosphorus, and it depends on the animal species, age, and diet, and also how manure is being stored. There are different kind of fractions in the manure. That means organic phosphorus, inorganic phosphorus, some water-soluble phosphorus, and these also vary greatly. For example, around 80 to 85% of the phosphorus in liquid swine manure is in the inorganic form, and the rest is in the organic form. So inorganic and more reliable organic form in the manure become readily available for crops after it's applied in the soil, and water-soluble phosphorus may be retained to a different degree to the soil. So manure from swine farm has an average nutrient value of $30 per $30 to $35. Now I think it's increased more per 1,000 gallon based on the potassium, phosphorus, and nitrogen content. Around 10 to 5 pounds of phosphorus, 20 to 30 pounds of potassium, and 40 to 50 pounds of nitrogen per 1,000 gallons of manure. And it has been estimated that around 75% and 60% of states available manure, nitrogen, and phosphorus is coming from the swine manure. However, swine has several issues. So now in the left side, you can see a farm where the manure has been stored, and they have several issues of ammonia volatilization, ammonia, smell of ammonia, and they have to transport the manure and applied it in the field. And liquid manure application cost around 0.022 0.02 gallon per mile, the manure is transported. This may not sound like much, but it means that manure nutrients never travel more than 3 miles from the farm they are excreted on. For large farm, this means nutrients concentrated around the facility, around a 2 or 3 meter diameter, 3 mile diameter. This has led to concerns of over applications and keeps farmers from getting full economic value from their manure. Also, from the manure, there are several nutrients. I mean, suppose like nitrate, ammonium, orthophosphorus. It can lose into the water drainage, and it can release odorous ammonia and H2S gas. So it has been estimated by the United States Environmental Protection Agency that 15% of the greenhouse gas emissions are associated with the animal manure management in the United States agricultural sector. And so, 1 minute, what's going on? Yes. So what's the problem? The problem is the water quality issue. So that nitrate, ammonium, and also the phosphate, the orthophosphate from the surface runoff, it can accumulate in the water body and can cause a severe environmental damage. And this accumulation of nutrients in the water bodies often causes excessive algal growth, rapid increase in the phytoplankton growth, depletion of the oxygen level, and eutrophication. And this eutrophication actually decreases the water quality, ecosystem disruption, and loss of recreational value of water bodies. So I put 4 pictures of that in the top, and then top left picture is the eutrophication process and how it looks like when the lakes or in the stream get eutrophication, the blue-green algae. And the bottom left, it causes the Gulf of Mexico, the blooming, the dead zone. And after that, how the water looks like. So this is a serious environmental problem, accumulation of these nutrients. So, I'm sorry. So why is biochar considered in this study? So we may know that biochar is a recalcitrant carbonaceous solid obtained from the pyrolysis of the lignocellulosic biomass. So the biomass after pyrolysis, it produces biochar, and in the right side I put a scanning electron microscope image how it looks like. So it is very porous and high surface area material, and it has high absorption capacity, and it can act as a sponge towards nutrients. So potential use of biochar as an amendment to soil has several potential benefits, such as increasing cation exchange capacity, increasing surface area. It can increase the pH of the system, increasing plant nutrient availability, and it can enhance water holding capacity. However, biochar is diverse in nature. So different biomass produces different kind of biochar. And this heterogeneity related to the precursor materials, and it can result various unique physicochemical properties. And the porosity also vary, which can influence the absorption and biological interaction. Different biomass, feedstock, and different pyrolysis conditions determine the properties of biochar. So, as a conclusion, biochar can improve the physical and chemical properties of the agricultural soils and provide cost benefits by reducing water and nutrient losses. But it should keep in mind that biochar produced under different production processes. So, therefore, it has the potential to be produced and prescribed for a specific crop, soil, or substrate. In the next slide, I'm going to talk about different sources of biochar surface charge. So biochar has different surface charges, suppose like the electrostatic, the cation absorption, the ion exchange. But most of the cases, biochar surface charge is mostly negative. As a result, it is a poor absorber of oxyanions like nitrate or phosphate. So suppose like if you have a biochar and you are adding it in a nitrate or phosphate contaminated solution, it may or may not absorb that nitrate or phosphate. So it has limited anion exchange capacity to electrostatically absorb these phosphate or nitrate anions. However, biochar can be modified for high phosphorus absorption. So this is the publication from our group. I think it's published in last year, that in our recent progress in the autothermal pyrolysis, we are allowing some air so that partial oxidation condition can convert the iron salt into iron oxyhydroxides, which is capable of complexing phosphate. So what we did is that the corn stover biomass, we impregnated with the ferrous sulfate solution, and we did the autothermal or oxidative pyrolysis at 500 degrees C. We are producing some iron phases onto the biochar, and that biochar can absorb the phosphorus more strongly, which cannot be released easily. So we, in this paper, we show that this biochar can act as a phosphorus slow release fertilizer. Also, iron salt modification keeps the biochar surface pH in the acidic range, since iron is acidic, which is favorable for reducing the ammonia volatilization loss. In swine manure, nitrogen exists mainly as the ammonium form and secondarily as the nitrate form. So both of which are readily leachable and can be utilized as sustainable soil fertilizer upon strategic application. In the next slide, I'm going to show another progress from our group that biochar can be used for developing slow-release nitrogen fertilizer. So, partial oxidation condition of autothermal pyrolysis followed by the phosphoric acid activation stabilizes urea onto biochar. In this study, we demonstrate that nitrogen slow-release fertilizer pellets with high nitrogen loadings can be produced from urea into the engineered biochar using some binding agents and stabilizing agents. These developed slow-release fertilizer pellets can reduce the ammonia volatilization loss and can increase the ammonium availability and can reduce the nitrate loss to the leaching compared to the uncoated urea. So now, considering 10 to 78% loss of the applied urea in the soil, these slow-release fertilizer pellets have good prospects for being economically viable. Additionally, we have used the phosphoric acid in these pellets, which might add some cost. However, the phosphorus from the phosphoric acid in this slow-release fertilizer will be largely plant level, and hence the extra cost will be offset by a reduced need for phosphorus fertilizer. In the next slide, we also have shown that biochar swine manure mixture have positive impacts on soil quality and plant nutrient availability. So in this study, we used columns, and the treatments are soil, swine manure amended soil, iron corn stover biochar and swine manure amended soil, and corn stover biochar and swine manure amended soil. In this study, we found that this iron, the mixture of biochar and manure is actually increasing the various plant nutrients. Another proof of concept study, so we showed that this engineered biochar can reduce odor from the swine manure. So this is a superficial application of the biochar onto the swine manure, and we have shown that ammonia reduced around 40%, H2S reduced by 20%, paracresol reduced up to 97%, and skatol reduced up to 95%. So this biochar can be used to reduce the odor and also some volatile organic carbon from the swine manure. So another component in our study is the zeolite. So what is zeolite and why it is important? So from the Wikipedia, it says that zeolite are microporous aluminosilicate mineral. It's a natural mineral, commonly used as a commercial adsorbent and catalyst. So in the literature, researcher used zeolite as a active catalyst and as a dehydrating agent to remove some moisture from the system. But this zeolite can also be used to absorb some nitrogen. Zeolite contains both silicon and aluminum, which has a slightly charge difference. This after mineral weathering, the substitution of one silicon atom with one aluminum ion resulted with one extra negative charge. This negative charge can be used to trap positively charged ammonium plus ion from manure. That is the main reason we are considering zeolite as an active component for our system. So now I gave some introduction about biochar and zeolite. So how we can use this biochar and zeolite to build an integrated system that can provide both economic and environmental benefits to swine and agricultural industry. Now, the next slide is that engineered biochar and zeolite combination can recycle swine manure nutrients and slow release them into the soil. So from the liquid manure, biochar and zeolite can absorb some nitrogen and phosphorus, and we can process it is in a solid form of fertilizer or granules like urea granules, and we can directly apply it in the field. So the benefits are it can reduce the nitrogen loss, phosphorus loss, it can reduce the odor emission, and it can provide better ecosystem benefits to the agricultural fields. So our main innovation exploration is the integrated bioreactor system, in which we can collect the manure and we can treat it with biochar and zeolite, and we can process some anaerobic digestion to produce fertilizer to recycle after recycling the nutrients, which can control the odor, which can reduce the greenhouse gas emission, which can reduce nutrient loss, synthetic fertilizer use, and can improve water quality and build soil quality. So the proposed project will examine the potential use of an integrated bioreactor system to reduce the emission to the atmosphere and recycle the nutrients from manure for use in crop production, reducing nutrient loss to water bodies and to the atmosphere. So this proposed system presents an opportunity to provide economic and environmental performance of integrated crop and animal agriculture. So this brings our main objective is using a bioreactor system using a pyrolysis biochar bioenergy platform to provide economic and environmental benefits by increasing the nutrient use efficiency and improving air quality within the swine production system while reducing offsite nutrient leakage. And that is our overall objective. Now in this study, our specific objective is to address the biochar and zeolite or mixtures of these two in an integrated approach to achieve a low-cost nutrient-rich products from the swine manure. So before I go to the next slide, I would like to transfer to Chumki. So she will talk about our next slides about our experiments results. Thank you.
Hello, everyone. This is Chumki Banik, and I'll be talking about an experiment that we did. It is kind of preliminary study just to check how efficient this biochar and zeolite and their mixtures are to remove or not remove, but recover those nitrogen and phosphorus from swine manure. So the swine manure we used had a pH of around 8. And because these manure has lots of colloidal material, and at the beginning I did a batch study to reduce the amount of solid. I centrifuged that manure at 7,000 RPM for 10 minutes, and it separated about like less than 1% of the solid material. And then that liquid manure was used for the batch study, and the manure had like 254 ppm of orthopy and 3,000 ppm of ammonium. Because ammonium stayed in the liquid phase mostly, the total manure had the same amount of ammonium, but the orthopy was a little higher. The total manure had like 410 ppm of orthopy. And then the iron biochar that I used had a pH of slightly acidic, like 5.4. And then the control biochar had a little alkaline, is 9.2. Both are prepared from Constover biomass, but the iron biochar was just iron pretreatment. I think it's Santanu already explained that how that biochar act as a phosphorus, how it can absorb phosphorus from the water media. So here I am checking whether it's capable of absorbing phosphorus from manure or not. And the biochar, iron biochar, had a 0-point charge of 4.8. That means the 0-point charge is like below which the surface is negatively charged, and above which it's like positively charged. So here is the first absorption study on the orthopy, and it shows that it can reduce actually the both iron biochar and control biochar. It can reduce the it can recover the orthopy from the liquid manure. Although the aqueous media was much effective, but as manure is a soup of various ions other than phosphate, so there are other competing ions that are making these orthopy absorption on this iron surface little less. And on control biochar, I believe that control biochar is absorbing through co-adsorption. That means when you increase the manure, you get more and more absorption, and that's why it has less absorption from aqueous solution. And how I am saying it's a co-adsorption rather than specific, it's because the desorption. So when we did the desorption study, the iron biochar was holding the orthopy much better than the control biochar. The control biochar released almost 80-90% of the orthopy absorbed from the manure, and the rest of the amount that is holding, that could be on the calcium or magnesium or the ash material that the biochar always have. That's the default. And we looked at the pH impact, and the pH shows that below pH 8, control biochar didn't absorb any phosphorus. And then when we increase the pH, it absorbed almost like iron biochar, and that could be because of these iron and magnesium, all those alkaline cation metals that is absorbing the orthopy, because they are very good at absorbing those absorbing orthopy. And this is the ammonium absorption study. So ammonium, we had around 3,000 ppm, and the aqueous solution we used was like 1,000 ppm. So both ammonium, both iron biochar and control biochar were good in absorbing ammonium from manure than the aqueous solution. And again, it's the co-adsorption possibly rather than because the co-adsorption is whenever you increase the manure solid content, the ammonium gets sorbed. At first, it started sorbing on the biochar surface, and then when it's covered with colloidal material from manure, it's sorbed on the manure solids. But the desorption was interesting. So we saw less ammonium dissolved when we increase the amount of manure. That means, so there could be several things happening here. So when we had low manure load, it could be sorbed on the biochar surfaces, but as we increase the manure load, so we are going at higher pH, and then at pH above 9, ammonium cannot stay as ammonium. It becomes ammonia, volatiles. It could lose into the environment. Or there are studies that show that biochar can actually immobilize nitrogen. So we don't know at this point what could be happening, but we saw less desorption and than like only 10% or less of the dissolved ammonium. And then we looked at the pH impact on ammonium absorption. So at low pH, both biochar was sorbing equal amount almost. And then when we went to a pH 6, pH 8, the iron biochar was more effective. And I believe it's because of the PZC that I explained earlier, that iron biochar has low PZC, which means like iron biochar was negatively charged at the pH 6 and 8, but at that pH, the control biochar surface was positively charged, and that's why it didn't absorb any ammonium. And then at pH 10 or 12, again we are seeing high absorption for both biochar. So and at pH 10 or 12, ammonium doesn't stay as that, so it could be lost into the atmosphere, and maybe that is what we are seeing, or maybe it could be trapped into the biochar pores. And then this is the zeolite, iron biochar and control biochar. This is comparing their efficiency. So which shows that zeolite was not as effective removal of ammonium from manure in comparison to iron biochar and control biochar, but still it absorbed quite a bit. And this is the orthopy adsorption on biochar in the integrated in the system where we used biochar and zeolite. So okay, this one is like I had biochar and then I added manure and I centrifuged that and decanted the solution, and I did that like 15 times. And after that 15 times, the liquid manure I analyzed, and I found like the iron biochar absorption and desorption was did this similar kind of absorption desorption as I had the batch study. So, and then for the zeolite, presence of zeolite doesn't absorb phosphorus, so it only absorbs ammonium because the zeolite surface is specifically designed to absorb ammonium. Here, when we introduced zeolite, it showed that we increased 82 milligram per gram of ammonium absorption on that iron biochar zeolite system. And the same way, the control biochar zeolite system had 58 milligram per gram of increase. So the bold color is showing the absorption, and the light color is the desorption. You can see like the absorption is always higher than the desorption. And the desorption is another, like why we are seeing less ammonium in this desorption is because could be it's forming struvite, because we did some XRD analysis, and it showed that the biochar zeolite system we had, we saw some struvite precipitated on top of biochar. Although when we centrifuged the manure itself, we didn't see any struvite or anything formed in there. But when we did that in presence of biochar, both like iron biochar and the cornstover biochar without any iron treatment, both showed presence of struvite. And that could be why the ammonium in the solution was less, the desorption study. So the overall summary is like these manure, the biochar zeolite, they can actually absorb both ammonium and orthopy. And the ammonium absorption was mostly electrostatic absorption. And that's why you generally get all the ammonium out of this biochar or zeolite. But here, as we are moving that ammonium to the struvite, and that's why maybe it's not coming out. And for orthopy, the iron biochar was absorbing as having like more specific absorption, because iron and orthopy has like they are good in chemistry. And then when the biochar, when the manure load increased, the absorption was more happening on the colloidal part of the manure. And that's why we were recovering the significant amount of nutrient P and nitrogen. But after application, maybe those will be readily plant available. But again, the transport will be easier. And this is our integrated biochar zeolite system that we are thinking to have, is like where we will pump that manure to this system where we will have iron biochar zeolite, or they're together, and then looked at the absorption desorption experiments and see how efficient they are when they work together. And with that, I would like to thank USDA for providing us the fund, and everybody in our group and other labs who help us with the sample analysis. And that's it for today's talk. And with that, I will ask Liz if anybody has any question for me or Santanu.
Yes, thank you so much. So again, for those of you that have attended for a CCA credit, please email me by 5 p.m. today. I'll be putting my email in the chat box for that, but you can see it there. It's ejuchems@iastate.edu. So the question came in, curiosity, how energy intensive is this biochar zeolite manure treatment?
So at this point, as we are doing mostly batch study, we haven't put that much energy into it. But yes, that's a good question, because when it will be from the farm, pig farm or something, then it will be more like of that energy question. So when we will have that study, I'm sure we will have the answer. But now, right now, it's like more preliminary work. It's like batch study and like lab study, you know.
So the goal would be that on site at the hog building, there'd be this mixture of biochar and zeolite happening, or would that manure need to be transported somewhere?
Yes. Actually, that's the goal. Maybe within 1.5 or 2 years. So we actually go to the real swine farm, and then we set up the system where we can input the swine farm manure in one side and then pump it through several columns and pass it through the biochar and zeolite, and then at the effluent we will taste it, how energy efficient is on the whole process. But you know, that means that the whole process is still at the bench scale level, so it's very hard to answer now.
And so just a clarification, the source of the biochar is corn stover, but how is that being treated and transformed into biochar?
Oh, very good question. So we are treating the biomass from the corn stover. The biomass, we are soaking it with the iron sulfate solution for several days to allow the diffusion of the iron and the sulfate ions into the biomass. And then we are pyrolyzing it, autothermal pyrolysis process at 475 to 525 degrees C. Autothermal pyrolysis is the first pyrolysis process. And then we are converting it into 3 different products: the biochar, the solid product, the bio oil, the liquid product, and the gaseous, the syngas. So we are collecting that solid product, which yields around 18 to 21% of the biomass. We are using that biochar. Does it make sense?
A little bit. So the naivety here, is this a similar process to like charcoal?
Yes, it's similar like charcoal, but we are making this in a different way, or different, you can say different technology. So it's called autothermal pyrolysis. So we have our pyrolyzer here at the Bioeconomy Institute, and we have out of the firm at the BioCentury Research Firm to produce the biochar. Recently, we have upgraded our system, and we are working with Harry Stein to make it to feed the 50 tons of biomass per day. That means we can produce 10 tons of biochar per day. So we are in process to licensing the whole system.
So question came in, is the manure treated while still in storage? So I'm assuming under the livestock or in a separate tank. And how do you think that treatment would affect greenhouse gases from the stored manure? So 2 questions.
Okay.
So at this point, as we said, like we are looking at the nitrogen and phosphorus. So one step at a time. Right now, we are trying to recover the nutrient. So this is the manure we collected from the storage, and they were at below 4 degrees C during analysis. And then we are trying to recover. Like at first, we are trying to see how much we can actually recover, using biochar and the zeolite integrated system. And then we will, from this bench scale, we will take it to the larger scale. And yes, before moving to the larger scale, we will do those greenhouse gas emissions. We will check on those. But at this time, we are working on the nutrient separation first, like how much we can actually separate, or it's feasible or not.
And so then by knowing how much can separate, that would be knowing the nutrient content,
yes,
the application rate.
Yes, and then if we can recover significant amount, which we are seeing, like yes, it can. So then the question will come, like how the environmental thing will happen, like when we apply that to environment or soil, how it will work on the greenhouse gas emissions.
So you noted that the average distance that manure is hauled is about 3 miles. So this could expand that radius of application. Could it also help with the timing?
Yes, I think so. I think so.
Storable?
Yes, I think so, because if we are stabilizing the elements that are like ammonia volatilization loss, right? And then it also help with the odor remove or odor suppression. So if we can work on those, that means we are giving a longer time for these manure biochar to store, and then we can apply like inorganic fertilizer, but it will be organic version of the inorganic fertilizer. Like you don't have to apply in the fall or in the spring. You can apply when your plants need that.
Yeah, and it can kind of eliminate some of that squeeze on hog producers when they're trying to have ground available when the pits need to be emptied.
Yes.
Pretty important.
Yes.
And also one point should be noted that the swine manure is a voluminous thing. That means it's a gallon after gallon. So if we can separate out that nitrogen and phosphorus, and we can form in the solid forms, maybe with the biochar and zeolite, and we can make the granules, so it would be very easy to transport. That means suppose like with a bucket, you can just carry several buckets of fertilizer and you can apply it in the field. So you don't need to carry gallons of tanks of direct manure.
How readily available is zeolite at this point?
Okay, so zeolite, normal zeolite or natural zeolite, if you say in that way, it is available at low cost. But in this study, we are using a specific kind of zeolite. You can say engineered zeolite. But we have a plan to use the normal zeolite also to check how much that means how much credits we are getting instead of the engineered zeolite. But natural or normal zeolite is available. It's not that much cost.
Is that something found here in Iowa or elsewhere that would have to be transported here?
No, not in Iowa. Not in Iowa. It's from outside the state.
So zeolite is increasing the efficiency of the system for sure, and that was our plan for the bench study. But at first we need to see like without zeolite also the system is working the same way, but it's just that improving. So here at this point, we are working on evaluating like whether we should have it or not. And then we will do the economic study of the whole system. And if we see like it's more, it's not important to add zeolite, and without zeolite, we can recover significant amount, then that will be our goal. But yes, at this point, zeolite is just improving the system.
So staying on that topic, someone's curious, what do you do with the zeolite catalyst after the reaction? Is it regenerated and reused, or is it tied in with the?
Okay.
Yes. So the phosphorus and then nitrogen, those will be directly applied to the field, like fertilizer. And for the zeolite, yes, we will try to regenerate the zeolite to use them again. And because that's easy enough to do, but right now, as I said, like we are working on the recovering part mostly.
And maybe this is preemptive too in terms of potential field studies, but curious, have you thought about collecting biological samples to evaluate the effects on microbes in the soils where these treatments are applied?
Yes, Biochar has shown to be effective in holding microbes, like, you know, to some extent. So yes, we have a long-term goal to look at all this stuff, because these we have field study that's in the plan, that we will do field study applying these, and then collect soil sample, and then water sample, everything, and then look at all these microbial work and everything. Yeah.
So testing in the lab right now, and then
yeah,
we'll be getting to field scale here in the future.
Yeah. So lab scale, then farm scale, then field scale. Okay.
I think final question here, tied to your carbon source for this biochar. So right now you're using corn stover, but any plans or tests on ways in the future for like wood or prairie grasses, miscanthus, other plant material?
Yes, that's a very good question. So corn stover actually has a lot of ash components. You know, that means a lot of alkaline and alkaline earth metals, maybe sodium, potassium, calcium, magnesium, and the wood source, they don't have a lot of these ash components, just silica. So we want this sodium, potassium, calcium, magnesium in the biomass. When you are using that biomass to produce the biochar, so it is producing ash, and that ash is actually helping to bind some phosphorus also, besides iron. So we tested in my study that I showed for the phosphorus study, the iron treated biochar. We found that the wood source biochar is not that capable of absorbing phosphorus. But if we use red oak corn stover iron treatment, that is more effective. So if you compare corn stover iron treatment versus red oak iron treatment, I would say that corn stover iron treatment would work much better towards phosphorus than red oak iron treatment.
Also, like in Iowa, we have lots of corn stover, so it's like we don't have to like get the red oak or any wood biomass from somewhere else. Like we have plenty of this corn stover biomass, and that way we can also help the farmers here to use those biomass for further study, you know.
All right. Well, it sounds like there's some great work coming down the line as you continue to work on this project. So stay tuned. We might look to invite you back once you get to your field trial scales, and then we can see what's going on with this project as well. So if folks are curious about learning more, where can they go?
Okay. So you can email, like we can share our email address. You can directly email us, and then we can help you with any questions you have, or yes, that will be best, right?
Yes.
So maybe if
we can share our email ID in the chat section. Is that okay?
That'd be perfect. And I hope you all can join us next week as we learn from Lindsay Hartfield here in the ABE department at Iowa State, the Ag and Biosystems, on pump denitrification bioreactor system for treatment beyond subsurface drainage. So thank you all for tuning in today, and thank you both for presenting on this very interesting topic. And we look to learn more as you continue your research.